What is up, Class 10 champions? Welcome to this ultimate revision session. Our mission today is crystal clear. We are going to completely decode the metals and non-metals science chapter so you can absolutely crush your upcoming board exams. In this fast-paced explainer, we're covering every single crucial concept, locking it straight into your brain. So let's not waste a single second and dive right in.
Here is our exact roadmap for today. We're conquering this in 6 simple steps. We'll start with properties and key exceptions, move into chemical reactions, break down the reactivity series, look at forming ionic compounds, dive into metal extraction, and finally wrap up with preventing metal corrosion. Section 1. Properties and key exceptions. Now, to truly understand anything, you gotta know what it looks like on the outside first, right? So let's establish the fundamental differences between metals and nonmetals.
All right, let's start with the absolute basics. On one side of the ring, we have metals. They're malleable, meaning you can hammer them into thin sheets. They're ductile, so you can stretch them into wires. Plus, they're lustrous, super shiny, and fantastic conductors of heat and electricity. On the flip side, non-metals are pretty much the exact opposite. No shine, no wire-making ability, they're generally soft, and they're pretty terrible at conducting electricity. Super straightforward, right? But hold on a second, because board exams almost never ask about the simple stuff.
Instead, you need to save these crucial exceptions to your memory's hard drive right now, because these are your ultimate exam hacks. In science, the exceptions often matter way more than the rules. We just said nonmetals are bad conductors, right? Well, graphite, a form of carbon, is a nonmetal that actually conducts electricity. We said metals are hard, but alkali metals like sodium and potassium are literally so soft you can cut them with a butter knife. And mercury? It's a metal, but it's chilling as a liquid at room temperature. Examiners absolutely love setting traps with these exceptions, so do not let them catch you off guard.
Section 2. Chemical reactions explored. Okay, we know how they look physically. Now let's see how these elements actually behave when they start mingling with other chemicals.
Imagine how metals react with water as a staircase of intensity. At the very top, you've got sodium and potassium. These guys are so wild they react violently with just cold water, literally causing hydrogen gas to catch fire. Take a step down the stairs and you've got magnesium, which needs hot water to get going. Step down again, and metals like aluminum and iron will only react with steam. And a quick pro tip here, they form oxides with steam, not hydroxides. Finally, at the very bottom of the staircase, gold and silver. They are completely unfazed and won't react with water in any form.
So, if gold and silver are incredibly stable and ignore water and normal acids, is there anything on Earth that can dissolve them? You bet there is! Enter another massive exam favorite, aqua regia. This is a freshly prepared, highly corrosive mixture of concentrated hydrochloric acid and concentrated nitric acid, mixed in an exact 3-to-1 ratio. It is so ridiculously powerful that it can dissolve those top-tier, stubborn metals that ignore everything else.
Now really quickly, let's talk about nonmetals and oxygen. When metals mix with oxygen, they create basic oxides. But when nonmetals react with oxygen, they form either acidic oxides, like carbon dioxide, or neutral oxides, like carbon monoxide. It sounds like a tiny detail, but this difference plays a massive role in chemistry. Moving right along to Section 3, the reactivity series. Get ready, because this is the ultimate cheat sheet for predicting chemical reactions. Now, let's talk about the reactivity series. The rule here is brutally simple. The higher a metal is on this list, the more powerful and reactive it is. These top-tier high reactivity metals are the heavyweights. They will literally kick bottom-tier metals right out of their salt solutions in what we call a displacement reaction. For example, iron can easily displace copper because it sits higher up the ladder. And those guys at the very bottom? They're so unreactive that we just find them chilling in their free state in nature, like pure gold. Section 4. Forming ionic compounds. Let's shift our focus. What kind of magic happens when a metal and a non-metal finally team up?
How do they actually bond? Through a direct transfer of electrons. See, metals have extra electrons they are desperate to lose, and nonmetals need electrons to become stable. So it's a perfect match. When sodium hands over its extra electron to chlorine, they both achieve perfect chemical stability. This direct transfer creates what we call an ionic bond, giving us super stable elements like everyday table salt or sodium chloride.
You absolutely need to have these 4 key properties of ionic compounds at your fingertips. First, they are rock solid and hard, because the electrostatic forces pulling them together are incredibly strong. Second, because of those super strong bonds, it takes massive amounts of heat to break them apart, giving them very high melting and boiling points. Third, they dissolve easily in water, but absolutely will not dissolve in solvents like kerosene or petrol.
And fourth, put a massive star next to this one. Do they conduct electricity? Yes, but only when they are melted down or dissolved in water. As solids, they are complete insulators because their ions are locked in place and can't move around.
All right, let's step out of the lab and into the real world for Section 5, metal extraction processes. How do we actually pull these metals out of the earth? You can break the dense concept of metallurgy down into 3 totally manageable logical steps. Phase 1 is the enrichment of the ore. This just means digging it up and cleaning off all the unwanted dirt and sand, which we scientifically call gangue. Phase 2 is taking that concentrated, cleaned up ore and converting it into a raw metal. And the method depends entirely on how reactive it is. Finally, Phase 3 is refining. This is where we purify that raw metal, usually using electrolysis, so it's 100% pure and ready for real-world use.
Now, roasting versus calcination. These are 2 terms that constantly trip students up, but here's an easy trick so you never mix them up on test day. Roasting has that strong S sound in the middle, right? So remember, it's for sulfide ores, and you do it in the presence of excess oxygen, kind of like roasting a marshmallow in the open air. Calcination starts with a C, so it's for carbonate ores, and it's done in the absolute absence of oxygen. 2 completely different methods, but they share the exact same goal, converting the metal into its oxide form.
Once you have that oxide, your strategy to extract the pure metal completely depends on where it lives on our reactivity series. Low reactivity metals like mercury, super easy. Just heat the oxide and the pure metal separates out. Medium reactivity metals like zinc, they need a bit more help, usually a reducing agent like carbon to step in and strip the oxygen away. But those high reactivity metals like sodium, they hold onto their oxygen so tightly that chemical reducing agents like carbon aren't nearly strong enough. For them, we have to use intense electrolytic reduction, basically blasting them with a ton of electricity to force them apart.
And that brings us to our final stop, Section 6, preventing metal corrosion. We just did all that hard work to extract these metals, so how on earth do we protect them?
When metals are exposed to the environment, they fall victim to corrosion. For your exams, you specifically need to memorize these color changes. When silver reacts with compounds in the air, it turns black. When copper reacts with moist carbon dioxide, it develops this dull green coating. And our most common metal, iron, reacts with moist air to form that flaky brown layer we all know and hate as rust. But we can fight back. Run through this checklist of prevention methods, because it's practically guaranteed to score you marks. You can paint the metals, or use grease and oil to form a basic physical barrier against moisture and air. Then there's galvanization, an awesome technique where we coat iron or steel with a protective layer of zinc so the zinc takes the corrosion hit instead of the iron. And finally, one of the absolute smartest methods, alloying, which actually changes the fundamental properties of the metal itself.
So what exactly is an alloy? It's a completely homogeneous mixture of 2 or more metals, or sometimes a metal mixed with a nonmetal. Why go through the trouble of mixing them? Because it severely upgrades their properties. It makes them vastly stronger and highly resistant to corrosion. For example, mix copper and zinc and you get brass. Mix iron with nickel and chromium and you get stainless steel. The exact same stuff your kitchen sinks and utensils are made of, which basically never rusts.
We've covered a massive amount of ground today, from physical properties all the way down to metallurgy and corrosion. So I want to leave you with a conceptual question to test your brand new knowledge. Imagine you've been hired to build a giant bridge in a highly corrosive, incredibly moist environment. Which specific metal, alloy, or prevention method would you choose to guarantee that bridge lasts for 100 years, and exactly why would you choose it? Think about everything we covered today. Thank you so much for joining me in this Ultimate Explainer. Keep up the amazing studying and go crush those board exams.